Today, we tackle a problem that challenges our understanding of sorting criteria. Imagine you have a list of numbers, and you need to arrange them not by their direct value, but by a unique characteristic. How many 1 bits are in their binary representation? Then, if that count is equal by their original value, how would you approach this custom sort? The problem, sort integers by the number of 1 bits, asks us to take an array of integers. Our goal is to return a new array where numbers are sorted first by the count of set bits in their binary form, in ascending order. If two numbers have the same count of set bits, they should then be sorted by their actual numerical value, also in ascending order. The input array contains non-negative integers. A straightforward but inefficient approach involves creating a list of pairs, where each pair holds the bit count and the original number. For every number in the input array, we'd manually count its set bits by repeatedly checking the least significant bit, and right-shifting until the number becomes 0. After populating this list, we'd sort it using a custom comparator. This comparator would first compare the bit counts, and if they're equal, compare the original numbers. Finally, we'd extract the sorted numbers into a new array. This brute force method has a time complexity of big O of n log n, linearithmic time due to sorting, and big O of n space for the auxiliary list. The key insight for an optimal solution lies in leveraging built-in language features for bit counting, and customizing the sorting mechanism directly on the input array. Instead of creating an auxiliary list, we can use an in-place sort with a custom comparison function. Modern programming languages often provide efficient methods to count set bits, such as a popCount function. This function directly returns the number of set bits for an integer, avoiding manual bitwise operations. Our custom comparison function will take two numbers, a and b. It first calculates the popCount for both a and b. If these bit counts are different, it returns the comparison result of the bit counts. If the bit counts are the same, it then falls back to comparing the original numbers a and b. This approach directly modifies the input array, making it more space efficient. Let's trace this with an example. The array containing 0, 1, 2, 3, 4, 5, 6, 7, 8. We use a custom sort. When comparing 0 and 1, 0 has 0 set bits, 1 has 1 set bit. 0 comes before 1. When comparing 1 and 2, 1 has 1 set bit, 2 has 1 set bit. Since bit counts are equal, we compare their values directly. 1 comes before 2. Similarly for 2 and 4, both have 1 set bit. 2 comes before 4. 4 and 8. Both have 1 set bit. 4 comes before 8. Now consider 3 and 5. 3 is binary 11, 2 set bits. 5 is binary 101, 2 set bits. Since bit counts are equal, 3 comes before 5. This custom comparison is applied across the entire array, reordering elements based on these rules. After applying this custom sort to our example, the final sorted array is 0, 1, 2, 4, 8, 3, 5, 6, 7. This order is correct because it prioritizes numbers with fewer set bits, and then by their numerical value when bit counts are identical. You'll spot this pattern when a problem requires sorting based on a derived property of elements rather than their raw value, especially when a secondary sorting criterion is needed for ties. Another signal is when bit manipulation is explicitly mentioned or hinted at for sorting criteria. The time complexity of this optimal solution is big O of n log n, linearithmic time due to the sorting operation. The space complexity is big O of log n, logarithmic time, or big O of n depending on the sort implementation. Typically big O of log n, logarithmic time for quicksort's recursion stack. This problem highlights the power of custom comparators and built-in functions for efficiency. Try the next problem to reinforce these sorting patterns. If you found this helpful, please like and subscribe for more DSA insights.